top and bottom dead center on a crankshaft. And in the motor, that gives you a possible 40 to 50% more advantage that you don't have with a crankshaft. Here we have inside here 2 gears, and in the center of each of these gears is a clutch bearing, a clutch roller bearing. The one direction it locks up, and the other way it's in freewheeling. The other way it's locked, and it does that instantly. So by that little action there, we get rid of the top and bottom dead center on a crankshaft type piece of equipment. The one I have here is being triggered by a 4-way air valve, and the air valve action is tripped by a signal air burst. And I'm getting my signal air burst from these 2 copper valves that I've built myself, and I didn't get them designed real perfect, so it keeps me from getting the quick action that I need for a high RPM. So can you get a view of the rack?
Yep.
Or do we maybe get a little slow motion and then I can see it? So from the back and forth action of the cylinders, the lineal action.
Wait a second. Wait for a second till the compressor kicks off before you start talking.
I have to turn the air off.
Okay.
I don't have enough. See the teeth on the rack? I put a double rack in here, so there's one tooth working on the bottom gear and one tooth working on the top. That way it gives you an action here where these are going to stay in, going in one direction. Well, we don't want to turn that on yet. Also here, because we are going this way and having to make an immediate change of direction, we lose some momentum problems there, so I've added springs on the end. So when it hits the springs, why, it slows the weight of our rack and pistons down, and it stores energy. So when the valve changes instantly, why, the springs give back the energy they've stored. So it helps take this. You'll notice that this machine is just setting on its own weight on the table. In spite of the action there, it's not vibrating itself off the table. But it was doing a worse job before I put the springs in. We can't hear ourselves think on the video when the machine is running and the compressor comes on, but it's interesting to notice the action. I put some white marks on the gears here so you can see how the action goes, and you can, it starts to work at about 10 pounds pressure. Because my compressor is very small, I can only get up to about a 25. Sequence of the mark.
Boy, it is really smooth. You really did a nice job on that.
Look at the gauge there. Here we have like two little exhaust silencers on the valve here, but the noise with them out is not enough different to even take a separate picture of it. Now the problem that we have here is the pistons on these can run into the end of the cylinders, but I have here a way of, by moving the two signal valves here, and there I can protect so that the signal comes while the cylinder is in between the two ends. I have a total of 6-inch stroke, and I'm getting my timing by using 5 inches of stroke. So when you've seen the machine running, it's been using 5 inches of the 6-inch stroke that's in the pistons. And it's not a extreme loss there, because on the old steam engines they lost as much as 25% in the timing element of the weight of the engine and the pistons and the top dead center problem. So here, by loosening that, I can adjust those there. Now if we get into a higher speed, I'll probably have to have a mechanical way of adjusting these slightly, because the faster speed, you're going to have more momentum on the rack there. But it has controlled it well just on this prototype engine. I correct my valves here, and we've got an engine here by connecting here to the output shafts, a workable engine already. Now it's going to cost me a little time to design and build me a couple of 3-way valves, or purchase a couple, but the price on them goes up too. So I don't really have an extreme amount of money involved in the 2 gears. The clutch bearings only cost $28 a piece, and we are only using 2 of them in this model engine here. The problem is that the ones that you can purchase don't have enough torque, so I'm going to have to design my own clutch bearings. But the original idea that I've seen the clutch bearings happened about 50 years ago, and the clutch bearing that we had, that I got my ideas from then, was handling about 1.5 tons of steel in their index method with theirs, and it had only 1 roller, where these new ones, and where you can get a picture in there, see there's 3 sets of rollers in there. The center set are the locking ones. There's I think about 16 of them in this 1-inch bearing. This bearing will stand 930 some inch-pounds, but I need 1,000 foot-pounds in my engine that would run a full-size automobile. But the one that's on the machine 50 years ago had only 1 roller. It was about 1/2 inch. The outside casing of the bearing was about 3 inches. Oh, they're setting on the mill over here. In other words, a piece of iron like that, 3 inches around, I'm going to put about 4 or 6 rollers, 1/4 inch in there, and that should give me enough force and metal support there to run a 25 horsepower engine. So as you notice, the thing was not bouncing off the table, so we don't have to worry about that. So it looks like I have enough muscle here in this to drive something like a golf cart. So the next edition of our photography here, or whatever we call it nowadays, will show up next inside of a golf cart. Well, you can say yourself that you want to drive it.